Bismillahirrahmanirrahim. Assalamualaikum and hi. My name is Nurul Iman binti Asma Azmi Rashid. Today I will present about diverse features of Legendre wavelets. So, in a functional analysis, completely supported wavelets is derived from Legendre polynomials are termed Legendre wavelets or spherical harmonic wavelets. The Legendre functions have widespread application in which spherical coordinate system is appropriate in our life. So, we can present a dependable procedure in view of Legendre wavelet spectral strategy to get an approximate solution of our nonlinear ODEs on an arbitrary interval. And then our spectral method usually used in numerical solution of nonlinear partial differential equations. And also by using the Legendre wavelets, an approximate solution on each element can be obtained by spectral method. This spectral method gives the more high accuracy and stable algorithm with a small number of elements under a wide range of conditions. After that, when we combine the Legendre wavelets and quasi-linearization method, it help in develop a new numerical algorithm. And when we develop a computational and new method to solve, we can develop a computational and a new method to solve a system of two-dimensional Volterra integral equations by using the Haar wavelets and implementations of hybrid Legendre block pulse. So my research question is, what is the use of the Legendre wavelets in solving mathematical problems? So the objective is to extend the Legendre wavelet for more approximate solution of a class of Land-Imlin equations. Second, to develop a Legendre Tau-Galerkin for nonlinear evolution problems, and also to consider its multiple interval form. Third, to develop numerical algorithm by using Legendre wavelets and quasi-linearization method for simulation of multi-dimensional BBMB, which is Benjamin Bona Mahoney Berger and Sobolev equations. Fourth is to solve two-dimensional Volterra integral equations, which is very famous integral equations. And lastly, to present a spectral element method for numerical solution of Volterra integral differential equations with boundary conditions. So the first method is by extending the Legendre wavelet, which is appropriate for any time interval, cause Legendre collection points of the Legendre wavelet is acquired. Then the iterative spectral technique will convert the differential equation to a set of algebraic equations such as below, which is our fx, and this is one of the extended Legendre wavelet. And then second, we can shift the Legendre polynomial of degree k on I. Then we can put our ut that stated in my slide, our ut and vt into the is not a piecewise in this such as piecewise function, and it will lead to more simpler algebraic system that I explain detail in my proposal. So we can solve our equation more easily when our algebraic is simpler. I hope you can understand. And also by Legendre wavelets, we can evaluate an unknown function such as the first equation at the top, and also the second equations. It's too long for me to read it, and it will become like the third equation, like at the bottom. It is the very simple equation after we combine it. After we evaluate both of these equation, the two upper equation, it leads to more simpler equation that we can use to solve any mathematical problems. And lastly, this is not commonly used, but Legendre and Lobato polynomials can also be calculated using the recursive relation, which is this equation Ln plus 1 theta and also Lon minus 1 theta. So we have 4 big methods. So for the expected result, firstly, the domain partition and solution of a given initial value problem solution have been built on each interval. It is called an iterative spectrometer that is sufficient to obtain an approximate solution of initial value problems at any given interval. Second, an equation has been rewritten in a simplified form and can be resolved by some suitable iterations. So it helps many people, many other users to solve mathematical problems. And time spectrum method have also been developed for numerical solution of certain nonlinear partial differential equations, where the Legendre-Galerkin and Chebyshev method are also used in space. There are saling berkait method equations. Third, the time dependent of one-dimensional, two-dimensional, and three-dimensional Benjamin Bonner-Mahoney Burgers (BBMB) and Sobolev equation also have been resolved by using the Legendre wavelets. The wavelets can approximate all the temporal and the space domains. Fourth, the Legendre wavelets also solve two-dimensional Volterra integral equation 2dVIE, and the solution that we can get is more similar to reality, and the competition also low. So the solution after we use the Legendre wavelet is leads to an accurate solution because the error is very smaller. And lastly, the Legendre spectral element that has been constructed was used for discretization or also for the solution of the Volterra integral differential equation with boundary conditions. So as you can see, the Legendre wavelets is have many uses in mathematical problems. It can extend, it can be shifted, and it can lead us to more simpler algebraic and simpler equation that we can use to solve future problem. So I think that's all from me. This is my references, 5 references, 5 articles that I use. That's all from